Thank you. Thank you so much for taking your time for my session. What is ML Ops? The best practices for DevOps for ML. I'm Kaz. I'm a developer advocate, so it's like an evangelist for developers and engineers. I'm focusing on data and analytics products like a TensorFlow machine learning engine and BigQuery. I have been working at Google for the last 7 years. And what is ML Ops? Actually, I and my colleague has created this word. There was no ML Ops word, ML Ops. That stands for the DevOps for ML. And I have been collecting this concept or topics of the operating production machine learning systems for a couple of years, because I have been keep hearing from the ML expert that launching is easy, but the operating is hard. From customers and internal the ML experts. There's one ML expert in Google who has been supporting one of the largest ML service inside Google for many years. And he said, launching the first version of ML system is easy, but operating it for many years is the hardest part. So I thought maybe the practices for DevOps could work well for building the production quality ML systems. I copied this definition of DevOps from Wikipedia. It says, it's all about unifying the dev part and ops part, and strongly advocate automation and monitoring for all steps for the systems. So you can replace that part, IT part or system part with ML. So to build the production quality ML systems, it's important to unifying the ML development and operations and advocate automation and monitoring of the ML systems. And we have been publishing a couple of the papers in past, such as the ML machine learning, the highest interest credit card of technical debt. I call it as an ML technical debt paper. That was written by an ML expert inside Google who has been operating the large-scale machine learning projection system for many years. And they have learned many things in past over 10 or 15 years. And they have written the best practice as a papers. Another important paper is the rules of machine learning, or rules of ML paper. And with those papers and added with the other many episodes I have collected with the customers and customer engineers, I'm collecting many anti-patterns and solutions for the production machine learning systems. And I have 3 agendas for today. One is the anti-patterns for development time, patterns for the deployment, and operation anti-patterns. So let's start it with the development anti-patterns. The first pattern is the ML superhero. Maybe you have seen him in your company. He's a superhero because he is a researcher who understands everything like a mathematical model, what's happening inside his model. But he also has a skill set to build his own Apache Spark cluster by himself, to do everything from a preparation, data preparation, or the transformation training. And also, he has a skill set in build and operating the infrastructure by using Kubernetes, writing the Docker file by himself. And also, he can be a product manager who can write the design doc by himself. And also, he is very fluent in communicating with the stakeholders like CXO and executives. And he does it from the proof of concept phase to the production phase. He's a Superman, but he doesn't scale. So the first project would be awesome depending on that kind of hero. But if an enterprise or startup want to reproduce the same success with ML systems with many different features or the products or the divisions, then you have to hire that kind of superhero, tens of them. So instead, you have to build a team, scalable team, by splitting the roles into a much simpler roles. So you could have the multiple roles, such as the ML researcher, or data engineer, infrastructure engineer, product manager, and business decision maker. And let me show one example of the team.
OK, all right, so click on that and speak into the mic.
May I have some gum?
So it understood what you said, may I have some gum? Now it's going through natural language processing. It's identifying the noun there, and gum. So now it's trying to It will then match based upon the model that's been modified. Come on, come on, come on. And it is picking chewy gum. Oh, and there the camera identified extra long-lasting watermelon gum. Now the camera's and over, and there's your gum.
That's great.
Machine learning in an app.
So I get to keep this, right?
Yeah, actually I've got like 7 boxes back there, so please take it.
So that was the demonstration we have built for the IO and Next last year. So some of you may have seen this last year. And this was a demonstration, but for us, it's a production machine learning system. And I designed it. I have written a rough design doc for this by myself, and worked with the vendor called BrainPad in Japan, and who has expertise on building the production machine learning system for many years. So because I wanted to make a production quality demonstration, so I asked them to build a team for this. Because the I/O is not only the one venue for these demonstrations, we had to present this demonstration at many large events like Next San Francisco, Next Tokyo, and India, and many other places. So we cannot rely on the ML superhero. So the BrainPad had created a team with researchers who built the Word2Vec model running on TensorFlow for the candy recommendation, and also the image recognition and transfer running. And also software engineer who uses the ML APIs, vision APIs, not vision API, speech-to-text API, and NL API. Hardware engineer who focuses on how to control the robot precisely, and project manager who leads the team. And I was the business decision maker, communicating with all the other stakeholders like a marketing, PR team, and legal, everything. So that went well because the BrainPad has a practice to create a very tightly crossed, tightly coupled teams with the researchers and engineers as a one team. But sometimes you have this problem, a black box that nobody understands. If you create a machine learning team with the researchers and the engineers and infra engineers, it's possible nobody understands the whole system because researchers would create the first prototype with his or her Jupyter notebook, and then engineer takes that code, does the refactoring on that to bring it to the production. And then researchers would not follow what's happening in the production code. At the same time, maybe engineers don't much knowledge about what's happening inside the model itself. Then nobody understands what's happening inside the whole system, and it's really hard for the optimization as a whole system. So the ML technical debt paper says, at Google, a hybrid research approach where engineers and researchers are embedded together on the same team, that has helped reduce this source of friction significantly. So not only building a scalable team, but also it's really important to have a tight, close communication between the researcher and engineer to understand everything and share all the same resources like a code, a model, and model. And for example, maybe engineer can help introducing the scalable platform like a cloud ML engine, working with the researchers. And because you can do that because we have introduced a new feature, scikit-learn and XGBoost support on the cloud ML engine, not only the TensorFlow. So, for example, researchers can start using the scikit-learn on Jupyter Notebook to define their model, and then engineers work together to port it to the cloud ML engine. So let me show some video that is created by Steve Greenberg, my colleague, how you can use the scikit-learn on machine learning engine. So for the first part, maybe the researchers can get started with the Jupyter Notebook to define the usual scikit-learn model. So you can use the BigQuery for getting the training data from database, and you can use the ordinary API on scikit-learn to do the pre-processing or splitting data, everything. Yeah, it is splitting the data to the training data and test data. And you can also the pipeline API of scikit-learn to build the pipeline for training. And then call the fit function to train the model. and try the prediction and get the result. So this is the part researchers can do with the usual practice. And this is where you can get the help from the ML engineer or infra engineer. This is where you're copying the scikit-learn model to the Google Cloud storage so that the ML engine can read it. And also, you can use the ML engine command to define a version with that scikit-learn model running on the ML engine, like this. And finally, you can try running it with the ML engine. So it is trying to try the prediction with the scikit-learn model running on the cloud. And you can get the same accuracy. And the important point here is that by using the ML engine as the predictions, the serving infrastructure for your scikit-learn model, you don't have to think about much about the scalability and availability by yourself. Usually, there's a huge gap between the POC model, POC systems, and the production systems. You have to think about how to build your cluster with the Kubernetes and containers, and you have to think about the life cycle of each instance and containers. But by using the ML engine, it's much easier. And engineers can help that, working with the researchers to bring the POC code into production. So next slide. Next pattern is CACE, or change anything, changes everything. It's a very unique characteristic or the behavior of ML systems. It's an entanglement you can find in the ML systems. That means a single change, one change to one feature could affect all of the other features. Or single changes in the hyperparameters or any way you prepared your training data or feature, that could change the behavior of everything, like how you can do your regularization or running rate or sampling or threshold. That could change the behavior of the whole system. That's the reason why the ML experts said launching is easy, but operating is hard. Rules of the ML paper says defines rules 14th. Starting with an interpretable model makes debugging easier. And there's another rule, rule 14th. Keep ensembles simple. What is the simple model? So it's the deep learning model is so attractive. And you can say to the business people that we are using deep learning. It's an AI system. But sometimes the deep model makes things complex. So if you want to use deep model in your production systems, you can use that judiciously. Because linear model is much easier for debugging. It's much easier to train the model and get the global optima. Whereas if you are using the deep model, usually the model is non-convex. That means you are not sure if you are getting the best result from training or not. You have to make many trials. And also, it's important to make everything interpretable by humans, not having a black box. Another pattern here or solution here is to use ensemble models rather than using a huge one monolithic model. So if you have one big deep model that takes hundreds of the features from the system, then it's really hard to debug or troubleshooting against that. So one practice you can use is to have a smaller model, small and simpler model. Works just like a parts factory for automobile factory. And you could have another model that ensembles all the synthesized features from those factories. So it works as an assembly plant. And it's also important to have everything semantically interpretable model, so that the persons for the troubleshooting, like operators, can easily find what will be the problem, what will be the cause of the problem. Is this model, or this model, rather than having a gigantic one monolithic model where the trouble would be embedded in somewhere in the model. So this, I wanted to show this one demonstration called Compeki. It's an image classifier for the use case built by the ArcNet. ArcNet is the largest provider for the real-time auction for use case in Japan, and they handle over 5 million auctions per year. And they have built a TensorFlow-based image classifier specialized for the use case. So the users can upload all the different pictures of a car from different angles, like from front or back or side or tires or steering wheels. And then systems classify that. And you can get the car make and model name and classification of these images at high accuracy. They have built it, and it has been on production for over 2 years. And the one thing they did when they are building the production system was to split the model. So ArcNet initially created one big model, deep learning model, that takes all the features into it. But it ended up with splitting the model into the smaller model, so that they found they were able to do better troubleshooting or better optimization with the whole system. Sorry about that. Why is that? Does it work? Sorry. Okay. Let me try it. So it's much easier for the production systems on troubleshooting. So that was the pattern you can see in the development phase. And let's take a look at the deployment anti-patterns. The first pattern is lack of ML lifecycle management. The one scenario could be maybe researcher would start writing the POC with notebook, and he or she does everything on it from POC to production, like a data preparation, transformation, training, validation, and serving and deploy. And researcher got a high accuracy on the production service. But he or she would forget about the system after 1 or 2 years. So after 1 year or 2 years, maybe somebody found the accuracy dropping slowly. And director of the business asked the researcher to update the model ASAP, like by tomorrow. The researcher will somehow find the old notebook on laptop, tries to remember how to go through clicking all the cells, and do every process manually. And wonders, why am I doing the imagination programming? He or she is a researcher, and this is not his job. So solution is to think about the ML lifecycle management. So integrated job management, job orchestration, so that you can define all the components as a part of the whole job orchestration, starting from the data ingestion, analysis, and validation, training, and serving, and logging, and monitoring. Not as the ad hoc script running on the Jupyter Notebook. You have to build everything as a continuously deployment and repeatable infrastructure, and not depending on the researcher only. The one example of building that kind of workflow is using Argo. Argo is an open source tool for the workflow as a workflow engine for Kubernetes containers. So you can use this tool to build this kind of the orchestration for ML system. And actually, we have tried that for the one demonstration called AI in Motion. This is a demonstration you can find in the showcase area in the Moscow South, where we have the robot balls rolling on the table, and we have a smartphone Pixel 2 up above that takes all the images of the robot balls and running the object detection model of the TensorFlow Lite and control the robots by using the SDK. And this object detection model was trained at the cloud by using ML engine. And it also uses the reinforcement learning, the RL, to control the balls. So if you're interested, you can play by yourself by going to the showcase. And we had to build an ML pipeline or ML workflow because as you can see, it's very important to have the high accuracy on the object detection at every different venue. So each venue would have a different lighting environment, like the white lighting or the color lighting or strength of the lightings would be different. So it's important to be able to retrain the model and get the best result at each venue. So as long as you are using the Jupyter Notebook and using the manual process, it's not scalable and portable as a demonstration. So for this demonstration, we have built an ML pipeline by using Argo. So starting from the loading the training data and training and evaluation. And also, in this case, we have built a pipeline for converting everything into a TensorFlow write model, converting the TensorFlow write model and deploy the TensorFlow write files to the mobile devices. And let me show some example. This is the working Argo user interface for the AI in motion demonstrations. And the UI works just like the UI you have in the cloud data flow. So if you click one of the workflow, you can see what's the current status of the workflow, like what's the status? Is it succeeded or is it failed, or starting time, end time, and duration? Just like the things you can see on the cloud data flow. So by having this kind of orchestration tool, then you don't have to go through all the Jupyter notebook process by yourself manually. Instead, you can have someone like operators or engineers or the researchers pressing the buttons of the workflow, the Argo, to go through all the repeatable process and retrain the model and deploy it. Another pattern you could see in the deployment time is the lack of data validation. In the usual ordinary IT system, the behavior of the system is defined by the program code you have written. So you have to write a unit test to validate the behavior of your system. But what about the machine learning system? Because you are not writing the code for defining your behavior of your system. Instead, your system will be using data, training data, to define the behavior of the system. And how do you validate that? The solution could be the data validation tools. And one option is the TFX, or TensorFlow Extended. That is an open source tool provided by the TensorFlow team that provides the multiple different useful tools for the ML ops practices, such as the transformation for the data or the model analysis that I'll be talking about later, or the serving. And one of those features is data validations. At this point, we haven't open sourced the data validation part yet, but we hope to have it soon in the near future. By using TFX for data validation, you can easily define the configuration file for the data validation, such as the type and domain for each features or input data, whether it's a string or integer or what kind of range it has, or presence of the instances of each values, or valency, or distribution by comparing the divergence between two values. And if it fits into a certain threshold, then it's OK. Otherwise, you have to check whether your training data is OK or not. And TFX paper says we want the user to treat data errors with the same rigor and care that there is the bugs in code, because the data is your code in your ML system. Actually, the Google Play team has introduced the practice of data validation so that they were able to increase the install rate for applications for 2%. So lastly, I'd like to discuss about the anti-patterns you can find in the operation time. Sorry about that. Why is that? Is it working? OK. It's not updating. Maybe, yeah, we try connecting the. Is it working? It looks like it's not my laptop. Looks like they switched. Yeah, I can continue with the other laptop. Yeah.
Okay.
And can I use the clicker? Where's clicker? Oh, yeah, I have it. It's not working. It's slow. It's slow but working. Sorry about that. So lack of continuous monitoring. So the model, any kind of model would see the drop of the accuracy over time. Maybe it's going to be, it would take years or maybe quarters or months or hours, but the accuracy would drop. And if there's no practice for your team for continuous monitoring on your accuracy or behavior of your model, the first person who would notice the drop of the accuracy would be the end user or consumers. So they would be frustrated with the performance or experience, and the business team would notice that, and director asks the researcher to update the model ASAP again. So that's what you want to avoid. And this is another pattern, training serving skill. That means any single differences, like differences of the training data or pre-processing the method or the windows you specify between training and serving or POC to production, that changes the accuracy. Another pattern is the not knowing the freshness requirements. So each ML system would have its own freshness requirement. For example, if you want to build the news aggregation website, then you may want to update the ML model every 5 minutes to get the latest updates. E-commerce site item recommendation can wait for a couple of days or week until updating the models. The natural language processing for customer satisfaction measurement may use the same model for a couple of months or maybe longer than that. Voice recognition doesn't require any updates on the model. Object detection sometimes requires the retraining the model for every setup, as I mentioned in the AI in motion case. And rules of ML paper says, rule number 9, detect problems before exporting models. The rule number 8, know the freshness requirements for your system. And the solution could be a TFMA or TensorFlow model analysis. That is a new feature included in the TensorFlow to do analytics on your model. And by using TFMA, you can follow some practices or rules, such as the rule 24, measure the delta between the models. Rather than watching the single accuracy of the current model, you have to see the changes or trend between the different models in time series. How the accuracy would be trending. Is it increasing or is it decreasing? And another practice you can use with TFMA is using the slice metrics for better model analysis. Not only using the single ROC or AUC number, you can use the different types of the features or the windows of the features to get the deeper insight of the behavior of your model. Let me show some example of using the TFMA. This is where you're importing the TFMA library and defines the slices by using the API of TFMA, by using the Jupyter Notebook. And by defining the slices, in this case, the code is using Chicago taxi trip data for training a model for predicting the taxi fares in each trip. And the easiest way is to get the ROC curve or the accuracy on the whole model. But by defining different slices, like sliced by the hour in a day or day in a week or year, you can understand much more details about the behavior of your model. So now it defines the slices so that you can get the multiple accuracies for each slices. In this case, it's a time series. So you can see different accuracies provided for each slices, hour in a day. And the highest accuracy is achieved at the noon time, where you would have many taxi users. And once you have confirmed that your model works as intended, and there's no problem on the accuracy or behavior, then you can use the versioning of the models on machine learning engine. The machine learning engine provides the APIs and CLI to register multiple versions of your model and choose which one of the models you want to use as a default. So you can use those CLIs, command lines, or the APIs to define the models and use it as a default model. Another rules, the rules of the ML paper says, the second rule is the first design and implement metrics. So if you want to have capture any problems or want to capture any good things or good feedback from the customers, define a matrix to capture all of those behavior from your ML model. For example, Google Plus team has been collecting many metrics from the behavior user activities, such as how many expands per read, or how many reshares per read, or how many plus ones or comments per read. So all of these small metrics can be a good input feature for defining the goodness of post. So that was the final practice and patterns. So summary, the development anti-patterns. You cannot rely on a single ML superhero. Rather than that, you have to build a scalable team. And at the same time, you cannot build the ML black box. And you have to be aware that ML systems can have the CACE, or change anything, change everything's behavior. For deployment, it's really important to think about the machine learning lifecycle management by using the tools such as the Argo or the Cloud Composer. And also, you have to understand the behavior of the ML system is defined by training data and your model. Lastly, it's very important to keep monitoring and logging your systems. So it's very important to set up the monitoring toolset and define the refreshment requirement for your machine learning use cases by using the tools like a TFMA. And if you're interested in those practices, please take a picture of these links names so you can learn more about those practices with those papers. The ML technical debt papers, rules of ML papers, TFX, and TFMA papers. And I'd like to give special thanks to Amy Unlu, who's the colleague of my DA team, who's built this TFMA demo. Norihiro Shimoda collected all the customer episodes, and Keisuke built the Argo ML pipeline for the demonstration. So with that, thank you so much.